Hello, Internet. So, I am an actual scientist. I have a bachelor's degree in physics and astronomy. I have a master's in applied physics. When I was in college, I actually worked on some telescopes, did a few research projects. After college, I worked at a fairly prestigious research laboratory for about 5 years. I ended up leaving that so that I could work at what many people would argue is probably the most prestigious place for any scientist to work at. Now, I don't currently work as a scientist technically. I ended up leaving that. I guess you could say I'm a computer scientist now. I want you guys to know that I greatly appreciate what you're doing. Unlike Bill Nye and Neil deGrasse Tyson, who think that we need to make the world safe for our children to learn science by getting rid of you guys, I see that what you're doing is appreciating science, and it is actually helpful to the broader goal of science. I mean, I don't think there's any more noble of a goal than the quest for truth. I know there's going to be some people who, think that I'm a government shill, or that I'm a Jesuit, or I work for the New World Order, or something like that. But that I just want you to know that's not the case, for whatever that's worth, if you could take my word for it. That I'm here to help. I want to help you guys do good science. And I actually like a lot of, like what I've seen. I like a lot of you guys. I've been a fan of Rob Skiba since before he ever got into this. I think Jeranism is hilarious. I've been entertained quite a bit by a lot of the stuff I've seen. Especially like the videos like making fun of NASA. Those always make me laugh. So I'm definitely I definitely consider myself a fan. There might be parts of this video where I point out that some arguments that are being made are quite stupid, frankly. I don't want that to be looked at as an attack, because it's not. I'm really trying to help. The reason why I wanted to make this video, I've been very sympathetic to the flat earthers ever since I first sort of stumbled upon this. I actually get the idea of like wanting to understand something for yourself, not wanting to trust what somebody else says. That's the whole reason why I ended up getting involved and like wanting to study physics to begin with, was that I wanted to understand the world around me. I wanted to be able to figure things out for myself. I've actually reached out to a few like flat earthers in the past, like sent them some graphs and stuff. My goal being to help you guys understand how to figure things out so that you don't have to just trust somebody else, Like, I understand that, like, NASA lies a lot. I understand that, like, someone might give you some equation saying, well, this is how you calculate gravity. And it's like, well, I'm going to take your word for that. It's kind of ironic that when people say, like, well, how much the globe curves like 8 inches per mile squared, and everybody takes that for granted. What I've done is I sort of created like a script to sort of help guide me through this, because I've been wanting to make this video for a long time, and there's a lot I want to talk about. It's probably going to end up being long. So what I'll try to do is I'm not really like a content creator, so hopefully I'll be able to figure out how to put like title cards in. So we can separate it out. That way, if you guys want to fast forward, you'll be able to find like the different sections. But basically, what I want to talk about, just some general concepts, some general pet peeves. I want to address issues that I have with scientists that are out there. Then I would like to address various issues that I have with flat earthers. And then talk about some things that I find rather intriguing, that I think are very, very good arguments. See, the problem is, like, It's just like with the whole, like, proving that the Apollo missions were faked. People put out all these arguments, and some of them are very good, and then they have some very bad ones that are easily debunked. And what happens is the skeptic community, I guess the mainstream community, will then make some video or some documentary where they just attack all the really dumb arguments. They totally ignore the heart. So the point is that there's some really good arguments that could be made, I think, to at least draw question to the globe model. And I feel like if everybody stuck with those and stopped saying the same really stupid things, then there might actually be some progress. And then lastly, I want to talk about how you can prove the Earth is flat. So there's a few experiments I think that could be done that would prove definitively, and I think it'd be very interesting if someone did them. Okay, so the first thing I want to say is that you pretty much, in this world, when you try to understand things, you pretty much have two choices. You can trust an expert, or you can figure things out for yourself. In this day and age, it's becoming more and more difficult to trust, quote, experts, and it's becoming more and more difficult to even identify who the experts are versus people that are trying to deceive you. But what I want to point out is that if you're going to trust your own self, that you shouldn't rely on your intuition. A lot of the really bad stuff that I see is people will make these claims based on what they think is, and my point is that your intuition is often wrong. I remember in my high school physics course, my teacher would always do these sort of like demonstrations, and he would ask, so, like, what do you think will happen if I do this? And I was always the first one to raise my hand. I consistently got it wrong. This is before I learned sort of how the world works and how to take apart the world. Even though I did so bad based on my intuition, I ended up acing that course. I totally destroyed the grading curve for the class. Got 100% on everything. I'm not saying this to brag. I'm saying this to say that I was able to learn how to think about the world around me. Like, one example, like he had this long trough of water with this like little toy sailboat in it. He had this like handheld fan, and he walked up and he blew on it, and that boat just kind of went across. And he said, "Now, what do you think will happen if I take this fan and set it in the boat?" And my gut instinct was that, well, it'll just blow. It'll just, keep moving. And he set it in there, and it didn't move an inch. My whole point, really, though, is to test your intuition. Here's another pretty good example. There's a YouTube channel called Smarter Every Day. And I saw this clip where Destin, he was driving a minivan. He had all the seats taken out, and he had this like helium balloon tied to the center of his car. And he asked the camera, "What do you think is going to happen when I drive forward? Is this balloon going to tilt back, or is it going to tilt forward?" And naturally, I thought, as he drives forward, once he takes off, the balloon's going to tilt back. Lo and behold, he took off, and the balloon shifted forward. Now, that was before I understood, but like without seeing that experiment and seeing what happens. Once I saw what happened, it was easy to figure out what was going on. As he moved forward, all the air in the car got forced to the back, increasing the density. And just like buoyancy, it was denser air in the back. This helium balloon then went forward, just like how it'll rise. But anyway, my point is, if you're gonna, this is a long rant. My point is, if you're gonna trust your own intuition, test it. Make sure, if you do some experiments, you start looking at things, do some experiments. If you find out that your intuition is wrong, then take that to heart and learn more. What you shouldn't do is say, well, my intuition was wrong, but it must be because there's some, magnifying properties of air. Or, it's one thing to come up with a theory of why things are acting the way they're acting, but then you test that theory. And there has to be ways that, you can test that theory from multiple angles, or else all you're really doing is cherry picking. You're looking for things that help validate your cause and ignoring things that don't. Anyway, okay, so let me just go over a few sort of pet peeves that I have. One pet peeve that I have is when people will make sort of hand-waving statements like, buildings lean away from you as you get farther away. And that might be true on the globe model, but how much do they lean? You know, you don't have to just, like, we have enough intelligence to figure out what that leaning is. You know, you don't have to just, you know, if you're going to make some statement, try and figure out, you know, like, as you rise, if the Earth is a sphere, then our horizon should lower. Well, how much should it lower? You should be able to figure that out. It's like simple geometry. There's nothing involved in calculating that where you have to take somebody's word for something. Another big pet peeve that I have is when people say, like, there isn't any such thing as a conspiracy. They can't exist because you can't keep a secret, and all it would take would be for someone to come out and blow it wide open. Well, whenever I hear someone say that, all I can think of is that they're just repeating what they've heard somebody else say. I've heard people say that so often, I feel like they didn't come up with that on their own. They're just repeating what somebody else said. But if they actually did some critical thinking about it and thought, you know, how many millions of people in this world work in an industry where they have to keep secrets, and it's successful. The concept that you can't keep secrets is just stupid. There's plenty of examples, like during World War II, like something like 200,000 people worked on the Manhattan Project. You know, so, and then like the other thing is, like, there'll be some whistleblower, and it's like, okay, so what you're saying is, because there's no whistleblowers, that's your proof that there's no conspiracies. Well, yeah. And then you show them whistleblowers, and they're like, oh, that's just a conspiracy theorist. So, anyway, my point is that it's illogical to say that conspiracies can't exist. It is just a pseudo-intellectual way to not address things and not think critically. Another pet peeve that I have, is when people are like, you're just anti-science when you try to question things. That makes me so angry, because it is, you know, it is very scientific to question things. It's anti-science to treat it like a religion and to just believe what people tell you on blind faith, or you know, just, anyway, I don't have to get into that. I think a lot of people understand that. Something else I hear all the time: extraordinary claims need extraordinary evidence. I'm not really sure if that's true. People say that all the time. What is extraordinary evidence? And is an extraordinary claim just something that most people don't listen to? I don't know. I guess I have the problem with the concept of extraordinary evidence. I mean, it's either evidence or it's not. You know, you don't need, like, if you were pulling up, like, chests from the bottom of the ocean, like, you know, sunken treasure chests, and you found gold coins, and like hundreds of thousands of coins dated to the year 1600, and you found one coin dated to 1700. That one coin is enough to prove that that chest went into the water after 1700. You don't need extraordinary evidence. You need one piece of evidence. Anyway, and here's something else too that I've encountered a lot, is that someone will say something, they'll make some claim, they are then corrected, and then that only works for the next few minutes, and then the very next time they get into the same argument with somebody, they keep bringing it back up again. It's like, wait a minute, you know, now that you know this, stop using it as an argument. You know, if I've proven to you that this thing that you're saying is wrong, stop saying it. It really makes me think that they're not searching for truth, that they have some claim they can make that sounds really great and it works to indoctrinate people, and that, you know, there's some ulterior motive, there's some reason why they want to keep using it. It's not because they're searching for truth. So I you know, during this video, we're going to come across a lot of these. Basically, there's common arguments that are being made that are just flat out wrong. And what I implore any flat earther out there, if you're making content, if you're making videos, what I implore you to do is stop making some of these claims that are just wrong. My whole point is, now that you know this is wrong, stop using it. Okay, so we talk about some of my gripes that I have with scientists and like skeptics, atheists, etc. So one problem I've seen it in my career, and I see it all the time, is not understanding what your assumptions are. And it's also sort of goes hand in hand with not understanding the difference between what you know and what you've been told and you've just been indoctrinated into. When you're, if you're going to use some equation, here's the equation for gravity. If you're going to use some equation to try and invoke your argument, understand where that equation came from. Because there's always assumptions that go into that. I mean, I've seen, I think on like a Joe Rogan podcast, one of the guys, he's one of like those famous atheist types. I forget his name, but he was saying that, like, he was talking about that experiment that they did, like, in, I don't know, ancient Greece, where they put a stick in the ground and then, like, 100 miles away, another stick in the ground at the same time of day, measuring the angles. And he was like, I mean, that proved it, not understanding that the underlying assumption there is that the sun is infinitely far away or incredibly far away. He's been so indoctrinated into that thinking that it didn't even cross his mind the possibility that the sun would be much closer. So, anyway, I don't know how else to say that, but I don't actually expect that to change, because scientists are notorious for being just indoctrinated into their thinking, especially the more like engineering types. In school, the way physicists are taught is much different. We have to derive our equations. It's very common, like anybody who's taken physics courses, you might have a test where they want you to like derive the, like luminosity of this star given these properties or whatever, and then you have to sit there and cranking out your equation, and then there'll always be some follow-up question where it's like, what if, what would be the answer if the radius was blank? And like most people punch in the number into their equation they just derived. Whereas when you look back through all your derivation, you find out, well, actually, if the radius was this one value, then that invalidates my entire derivation. That's, I don't know, it's more common in like physics courses. So anyway, another thing is cherry picking data. I have a huge problem with scientists who do this. It's cherry picking data, it's throwing out data, like they'll have some plot, some scatter plot, and there'll be a few outliers and they just throw those away. If you have a good reason to throw out data, like you can figure out why this data was an anomaly, my sensor was malfunctioning, or some part of your experiment was invalid, then fine. If you're getting anomalous data, if it's rare, it won't affect your overall results. I mean, you would plot that anyway. Like if you're showing some plot, it's okay to have a few scatter points on there. If there's so much that it's actually throwing off your answer, then there's probably something there, and by throwing out that data, you might lose out on some major discovery. I mean, there's a lot of discoveries that were found throughout history that were based on anomalous events. A good scientist won't go throwing them out. This is something that you'll see a lot in archaeology, where they'll find something that doesn't fit and they'll just throw it out. And they can keep making the excuse that it's anomalous because they keep throwing it out. Whereas if they had been keeping those data points, by now, the evidence is overwhelming that a lot of the mainstream understanding of Earth's history and whatnot would be completely invalidated. Anyway, Oh, and I also want to add this, because this does sort of play into it. The idea of cherry-picking data, the idea of throwing out data or only using certain things, this is all related to this idea of just going to like IamRight.com so you can validate your own, if you only listen to the points that help validate you, you're just going to be in an echo chamber. You're going to strengthen your own, your own assumptions. It's not something that is it's not something that is conducive to wanting to seek the truth. It is something that people that are indoctrinated would tend to do. And this whole thing, the whole philosophy behind this flat earth thing, in my view, is seeking the truth. Which is one of the reasons why I've been so sympathetic towards it. And I'm not sure if I said this earlier in the video, but I probably should point this out. I am not a flat earther myself. I've always, sort of, I don't know, I don't know if I was like just indoctrinated or what, but I always agreed with the globe model. This whole flat earth thing came up and I started looking into it very, 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 very intensely. I investigated everything. I found lots of things I thought were intriguing. I never really fell over the fence towards flat earth theory, but I don't know. Needless to say, there are some interesting things to look into. That's all I'm trying to get at. But anyway, I would not necessarily consider myself a flat earther. And then something else too, like I see this a lot with, maybe not so much scientists, but the skeptic community, and that includes like atheists, is that they're very lazy pseudo-intellectuals. Like, they will come up with arguments based on them just like pondering for a second and think that should carry as much weight as somebody who has a PhD and has been studying things intensely. It's just it's just quite aggravating to be very dismissive of things and use hand-waving arguments when you really haven't even broken a sweat in thinking. So anyway, I actually don't expect very many scientists to be watching this. So maybe this is just more towards the flat earthers to understand that even scientists have big problems with what other scientists do all the time. Okay, so now we're at what's arguably the most important part of this video. And as you can see, this is a completely different time of day, and the lighting is now completely different because I'm a pro at this. So, I'd like to go over all the issues that I have with different flat earther arguments. I have a long list of, 20 or so things. These are either completely misunderstanding things, making bad arguments, making unnecessary arguments. But the important thing is that if you're going to critique or try to disprove the globe Earth model, you need to understand the globe Earth model. Because otherwise, if you say something about it that's just completely incorrect and then prove how that can't be true, you're basically just straw manning. So I'm going to do my best to explain everything as thoroughly as I can, so that you can understand and you don't have to, hopefully won't have to take my word for any of this. And some of these are more scientific and in-depth than others, but so let's just get started. So first of all, I've seen a lot of videos out there where people are using clips from this documentary called In Search of the Edge, and I just wasn't sure if everyone out there realizes that is a mockumentary. If you look it up, In Search of the Edge, it's by Bullfrog Films. It's basically meant to be making fun of flat earthers. And if you watch the whole thing, I think it's it's obvious because of the types of ridiculous things that are being said. Here's the sad part is there's some arguments in there that are supposed to be a joke, and people are actually using them in their videos. So I'll put like an image of the documentary or something up here, so that you can, so that you'll know exactly what I'm talking about. Now this is sort of related, but there's that one documentary called Astronauts Gone Wild. This isn't really flat Earth; it's more like NASA, faking stuff. But I've seen a lot of people use clips from that documentary. This is that documentary where the guy goes around trying to get astronauts to swear on the Bible. But if you actually watch that entire documentary, it's actually not a very good... It doesn't actually make a very good case about the Apollo moon landings being faked. If you watch the whole thing, you'll find out that most of the astronauts, most of the time, are actually acting very reasonable. And then, he'll do something, or he'll ask them if they'll, pledge, and then they'll do it, and then he'll change his request a little bit and ask him a second time, and then they'll get flustered, and then people will use that clip. But anyway, this isn't really about the NASA stuff, and this doesn't necessarily mean that NASA did not fake anything. All I'm trying to say, though, is that because that documentary, when you watch it in full context, doesn't really make a strong case, it can be seen as disingenuous if you're just going to use some clip out of that makes the astronauts look like they're lying, whereas if you watch the whole segment, it doesn't really look like that. So I think that you'd be better served not even using that. Okay, anyway, so the second thing, when people talk about how there's no gravity, that it's just density. The first thing I want to say about that is, why do you feel the need to address gravity? You should be able to prove or disprove the round Earth model versus the flat Earth model without even talking about gravity. But that, fine if you want to. But here's the other thing about it, though. When you say it's not gravity, it's just density. Denser objects will sink, less dense objects rise. I don't really see that as being any different than gravity. You're not really doing... See, what a scientist would do is they would observe the phenomenon of things going down, things rising. They maybe give it a name, gravity, or you might call it density. They then try to quantify it, which they've been successful. We have very good equations to describe the speed at which objects fall. That's well understood. Now, I guess if you take the position that there is no such thing as gravity, there's just density, you would use the exact same equation to calculate, to compute how fast things fall due to, quote, density. It's really not any different, is all I'm trying to say. The difference would be that mainstream scientists who use gravity or invoke gravity in their arguments have taken it one step further by actually doing experiments and measurements. It's just not very strong. It's not a very strong argument. I will say this, though. Scientists don't know what gravity is. They have equations for describing how things act, but this concept of this spooky magical force, no one really understands why it happens, but yet we all know that it's true. Everyone out there they experience gravity all the time. There's no question that it exists. Whether you want to call it density or they call it gravity, it's kind of irrelevant. I feel like I'm ranting here, so I'm going to move on. Now, this is kind of related, but I have it as a separate thing to address. It is this argument that gravity is just this magical thing that people will apply whenever they have a problem, whenever they can't explain something to try to make the round Earth model work, they'll just say, oh, it's gravity. But that's not really what... okay, let me say this. I think the reason why people will say that is because the perception that it doesn't follow any sort of pattern. Excuse me. So this is like, gravity is strong enough to keep us on the Earth, but yet when you're out in orbit, there's no gravity, and then when you're way at the moon, gravity is now strong enough to keep the moon going around the Earth, and the moon's gravity is strong enough to make the tides move, yet it doesn't make anything else move. So, but I think that there's a misconception, and that is that there's zero gravity when you're in space. That is not true at all. Again, this is according to the round Earth model. Assuming the round Earth model and assuming the space station exists, when the space station is in orbit around the Earth, when anything is in orbit, it's falling. There's actually still gravity. In fact, the force of gravity, according to mainstream and round Earth model, the force of gravity at the space station, which is about 250 miles above the surface of the Earth, is about 13% or so less than gravity on the Earth. So it's a little bit less than it is on the Earth, but it's not zero. It just appears to be zero because the space station and everything in it is all falling at the same rate. So this is just like the parabolic curve that the plane takes to simulate. It's actually simulating it pretty darn good because it is exactly the same thing. If you were to go up in an elevator and the cables were to snap and the elevator just drops and everything inside the elevator is falling at the exact same rate, compared to everything around you, you would basically be floating. So anyway, I don't know if that helps, but it certainly, once you understand that, it makes a big difference when you think of, like, it's not like gravity acts different at all these different like ranges. Like gravity, according to physicists, according to mainstream science, according to everything that people understand about things, it does behave in a very predictable way. It's smooth in terms of like the strength. As you get farther away, it starts dropping off in a linear or in a smooth fashion. It doesn't go from like having gravity to nothing and then something else again later. So I don't know if that helps, but again, I want to go back to this idea of why bother, trying to poke holes in gravity. It doesn't actually help the case of flat Earth at all. Okay, well, this video is taking a lot longer to make than I was planning on. Anyway, moving right along. Here's something that I think is very important. If you're going to do measurements for curvature, just do it over water. I shouldn't need to explain why, but this just goes back into the whole concept of understanding what the globe model teaches so that you're not just straw manning. So your best bet, if you want to do measurements of curvature, like objects dropping over the horizon, do it over water, preferably the ocean, large bodies of water. Take careful measurements, measure how high the camera is from the surface of the water. That's super important because you have to take into account the height of the observer. It's not 8 inches per mile squared. That's not the curvature. Exactly. You have to take into account the height. So, okay, so the Michelson-Morley experiment. This is a big one. I've seen in videos people say that the Michelson-Morley experiment proved that the Earth isn't moving. So I'm going to try to explain exactly what the experiment was, what it was measuring, why it was relevant, and what it actually proved or disproved. Because I feel like people will just say it proved the Earth isn't moving, and then they'll show some clip of the experiment without actually understanding anything about it. So the first thing to understand is that fairly recently, scientists had just discovered how to mathematically describe waves. This was actually a really big deal. If anyone had any doubts in my credentials, I've got a magic whiteboard that proves that I'm a scientist. Okay, so one thing that that people had discovered or had learned about waves is that waves exhibit properties of interference. So let me just draw out and try and give you a quick example. So if you were to, let's say you were to have a tight like rope, maybe tied between two trees or something, and you were to pluck it and send a wave pulse traveling down. So you induce a small wave pulse, sending it down towards the end. Well, let's say that somebody else on the other end also plucked it and sent a wave pulse going the other direction. What you see is, if you were to be filming this and watch it in slow motion and pause it at just the right time, you'll see that as the two waves cross paths, there's an instant in time where the two waves add together. And in this case, the two waves are in phase. So what you'll get is, once the two waves are passing each other, they're on top of each other, they add together, so you get a double the amplitude just for an instant in time, and then the very next moment in time they've now passed each other, and they just keep on going without slowing each other down. You can also have destructive interference, and this would be the case where your waves are out of phase, and in this case, as the two waves are passing each other, there's an instant in time, if you were to pause it, let's say, where as the two waves are right on top of each other, they cancel each other out. So you add it up, so the positive gets added to the negative, and it cancels each other out. Just for that instance, and the very next instant in time, they have now passed each other, and they go on their merry way. Okay, so that's part of it, the idea of interference. So scientists had noticed that light was exhibiting interference patterns. I don't want to get into that because it'll make this video much longer than it needs to be, but light was behaving in the same way, that it could interfere with itself and either become brighter or cancel itself out and become dark. So this told them that light is behaving like a wave. Light must be a wave. That's actually faulty thinking. It was behaving like a wave would be a correct way to look at it. But anyway, what scientists understood, though, is that waves need a medium to be traveling in, or waves need a medium. In other words, if there's a wave, something must be waving. In this case, the rope is the medium. The rope itself is what's waving. It's what's moving up and down as the energy pulse travels by. I think this is where their understanding was incorrect, because when you look at interference, the thing that is either getting bigger or canceling out is the thing that is waving. That makes sense. So in this case, the string is what's waving. The string amplitude is what gets increased or decreased due to interference. With light, it's light itself that gets increased or decreased. So their thinking was slightly incorrect, but nonetheless. So, okay, so we've covered that. So people tried to devise an experiment. So they said that if light is a wave, there must be a medium. Sort of like air is a medium for sound, there must be some medium. They called it ether. So that like the entire universe is filled with this ether, and that's the medium that light is traveling in. So they wanted to devise an experiment to measure the speed of the Earth compared to the ether. Okay, so this is important too. So let's just say that, sound is a wave in the air. If there's let's say that there's a steady breeze traveling this way at 20 miles per hour. A source of sound over there is going to be higher. It's going to sound higher pitched to me because the wave, the speed of the wave gets added to the speed of the medium. Since the air is moving and I'm not moving compared to the air, if the speed of sound is going by at 300 meters a second, you add that to the air so that when I'm standing here, I hear it passing by my ear faster. It sounds higher pitch. Okay, now the converse is if something is over on this side and there's air is blowing that in that direction at a constant speed and the sound is produced, I will hear it as being lower pitch because it's traveling towards me, but the medium is going that way. Now, if I were to travel with the air, let's say that the air is blowing at 10 miles an hour and I were to be traveling that way at 10 miles an hour, everything would sound perfectly normal. Okay, so if there was an ether surrounding everything and light was traveling through that ether, I should be able to, if I could make measurements of the speed of light in various directions. So if I can measure the speed of light this way and then this way, and maybe even for thoroughness up and down, which they didn't do, but doesn't matter. I should be able to measure a difference. If the ether is moving at a different, if the Earth is not moving exactly with the ether, I should be able to measure some sort of difference. And because the globe model says the Earth is rotating, if I do my experiment and then I do it again in 6 hours and in 12 hours, and then I do it at different times of year because the Earth in the globe model is moving around the sun, I should be able to run this experiment at all these different times, and if there is an ether, the Earth moving through this ether, I should be able to measure different speeds. Now there's a whole bunch of really interesting stuff about the Michelson-Morley experiment I could get into. I don't think it's important for this, but anyway, okay, so now when they ran the experiment, they weren't able to measure any difference whatsoever. So that told them basically three things. One is there is no ether. The second one is that there is an ether, but it moves with the Earth. That maybe the ether is very viscous, so that it sort of sticks to the Earth, so that as the Earth is moving through the ether, it sort of pulls it along with it. And then there was a third option, which I think it was Lorentz who had postulated that the actual arms of the Michelson-Morley device were contracting based on its speed, and it was kind of anyway. So, having that being said, so people say that the Michelson-Morley experiment proved that the Earth was not moving. That's not really true. It was set up under a false assumption, and that false assumption was that light needed some sort of a medium. Okay. Now, how do I know that light doesn't need a medium? Well, we talked about how with a wave, the medium is the thing that's waving. Okay, so with the string, the energy goes through the string, but the string itself is what's doing the waving. Same thing with air. When a sound wave goes through air, the energy passes by. The air itself is what's doing the actual waving. With light, the interference that they were measuring was light itself. They were seeing bright and dark patterns. So it's the light itself that's waving. And light is not a medium, right? Like when you send light, like a laser pulse, how can the pulse you're sending also be the medium? Does that make sense? Anyway, so point is, though, people, if they had thought about it, they probably would have figured that out. That and I should also add that we've since discovered that what is actually waving in a beam of light, there's a strength of an electric field and a magnetic field that's increasing and decreasing, and that's sort of unnecessary information to add. But anyway, it wasn't really a valid experiment. It's only valid if you assume there is an ether, there must be an ether. All that being said is, I would just stop using that as an argument, because anybody who understands the history and understands what the experiment was doing will not accept that as being a valid argument that the Earth cannot be moving. Okay, so this next one is it's a big one. I see it all the time. Everybody always says that the Earth is rotating at 1,000 miles per hour, and yet we can't feel it. Again, you know, people will refuse to take what scientists say at face value, but yet someone says 1,000 miles per hour is how fast we're moving, and everybody wants to use that because it sounds good. It helps their argument. You're not being consistent, though. You should think critically about that. Everyone out there watching this video knows how fast we're rotating. Okay, the Earth rotates once every 24 hours. Okay, that's very, very slow. Anybody who thinks that if they were sitting on a merry-go-round and it rotated once every 24 hours, that you'd be able to feel that, I beg to differ. Now, the reason why people say 1,000 miles per hour, again, this is based on the globe model, is that on the equator, if the Earth is rotating one time every 24 hours, then on the equator, if you can measure the radius of the Earth at the equator, the circumference of the Earth is 2 pi r, right? So that gives you the total distance traveled. Divide that by 24 hours, you get like 1,017 miles per hour or something like that. But that instantaneous speed is how fast a point on the equator is moving in a straight line, right? It's how fast that one point is moving, and everything around you, it's a constant speed. Everyone should know that when you're moving at a constant speed and everything around you is moving at a constant speed, so in other words, you're not changing speed at all, you can't tell the difference. You can't tell it if you're moving or not. Everyone should know that, right? Like if you're in a train and the train's going at 100 miles per hour constantly, you're not like being thrown to the back, right? Everything feels like it's just still. Anyway, so yeah, so that's the whole Earth rotating. And so something else you can think of is that if you know how slow the hour hand moves on a clock, the Earth spins two times as slow, two times slower. So it's a very, very slow rotation. You shouldn't expect to be able to measure that or feel that. Now what about, and then you also have like the Earth going around the sun, again according to the globe model. Well, how fast is that? Well, it goes one time, so 360 degrees around the sun in 1 year. So way, way slower than the Earth rotating. It should be imperceptible. You know, well, okay, so the whole argument is that you should be able to feel that. Your inner ear would be able to tell you that you're moving, that you're rotating. And I would argue that there's no way your inner ear would be able to tell you that. It is way too small of a speed. So anyway, now that you know this, though, I think you'd be best served if you stopped using that argument. So this is one of the big ones, though. Every time I hear it, I roll my eyes like, oh, there's the 1,000 mile per hour argument again. No, it's actually incredibly slow. So now that you know this, if you care about truth, then stop using it. If you actually care more about getting people to jump on your bandwagon, then keep saying it because it sounds good to people who don't know any better. Here's another one that's sort of related, and this is this idea that there's all these motions. So we've got the Earth rotating, and then we've got the Earth going around the sun, and then the sun is going around the Milky Way galaxy, and then the galaxy is going through the universe, and all these different motions, and yet the stars appear to be constant. according to the globe model, and I want to keep saying this so that, because again, you want to understand the globe model, so you take the assumption that the globe model is true, and then you debunk it. All right, you don't misrepresent the globe model and prove that wrong, or else you're just strawmanning. So, according to the globe model, yes, all these motions are happening, but here's something that a lot of people don't realize, and it's obvious once you think about it, but every single star that you see when you look up is in the Milky Way galaxy. Okay? It's incredibly obvious once you think about it, because we're in the Milky Way galaxy. Every single star you see is in the Milky Way galaxy. The reason why is because every other star is in some other galaxy. So you wouldn't see the star, you would see the galaxy. You would see some blob, right? Anyway, so all these motions, though, are... So when you say that the sun is moving around the Milky Way, well, that's because the Milky Way galaxy is rotating. So all the stars that are around our star are moving with us. So that's why you wouldn't see any relative changes with the stars. You do over long periods of time, because there are slight motions. There's incredibly large distances out there, so it has to actually, these stars have to move a large amount before you see any changes. So hopefully that clears things up. Again, it's not a very good argument. I would avoid using it. Let's stick to the good ones. Okay, here's another one. Buildings leaning away. People argue that, if you look far away, if the Earth is actually curving, that means that buildings far away should be leaning away. Well, how much should they be leaning? You should be able to calculate that. Let me just pull up the whiteboard real fast. This is an easy one. So if that is the Earth, I'm going to draw it exaggerated. So let's say you're standing here. Here's my stick figure. And there's some building there. Some distance away. Some skyscraper, right? So how far is that building leaning? So what you want to calculate to know how far that building is leaning is that angle right there. Okay? So if you know the circumference of the Earth, which is 2 times pi times the radius of the Earth, whatever distance this is, that distance of that building, think of it as a percentage of the circumference. Right? So if that distance was all the way around the Earth, it'd be half the circumference, right? So whatever that distance is, if you divide it by the circumference, so the distance over 2 pi r would give you a percentage of the full circle, right? Right? So if that distance was a full half of the Earth, that'd give you 50%. 50% of 360 is 180 degrees. The building would be leaning away 180 degrees. Okay? So to calculate that angle, calculate the percentage, times that by 360. What you find is that any distance that you can see is going to be less than a degree leaning. 0.0 something degrees leaning. It's not leaning very far at all. Not to mention, it's leaning directly away from you, so it's hard to see. It'd be one thing if it was leaning left or right, that'd be easy to see, but it would not be easy to see it if it's leaning away, especially by 0.0 something degrees. I have a little diagram that I will put up on the screen. Okay, so another common thing I see is people will say that you can see certain stars from the southern hemisphere, therefore the Earth must be flat. I would say, if this is true, get evidence of it, because yes, you will prove that the Earth is not round. If you can see Polaris from below the equator, then you've proven that the globe Earth model has a flaw with it. Every time I see somebody make the claim, they never back it up with evidence. They just say that. So I suspect that, yes, you can see parts of the Little Dipper south of the equator. It depends on how far south, but you can't, if you're like 20 degrees south latitude, you cannot see the North Star. If I'm wrong, get evidence of it, and there you go. Just, you know, all I'm saying is don't use that argument unless you have something to back it up, and if you have something to back it up, then only use that argument because you've done it. Okay, this is my third wardrobe change. This video is way too long. Nobody's ever going to watch this, but we're going to plow through it because this is very important. Okay, so a lot of times people will talk about the Coriolis effect or the Coriolis force. I don't think people really understand what it is. The Coriolis force is sort of a pseudo force. Probably the best way to explain it. Okay, so we had talked about the idea of along the equator, as the Earth rotates, you travel an entire circumference in 24 hours. And if you calculate that, you find out that the speed is right around 1,000 miles per hour. Well, if you go to some higher, like latitude, somewhere in like North America, let's say, the total distance traveled in one day is shorter because the radius that you're using for that calculation is actually shorter. Whereas on the equator, you've got the full radius. At some latitude, you have some shorter radius, and you can calculate that using trigonometry. But the point is that if you if you like fire a bullet north or south, once it leaves the ground, it keeps the same speed that it was traveling when it left the barrel of the gun. So if you're on the equator and you shoot a bullet north, when it leaves the barrel, it's traveling east at 1,000 miles per hour. By the time it reaches its target, the ground is not traveling at 1,000 miles per hour. The ground is traveling at a smaller speed. So what ends up happening is it ends up landing to the right. This is if you're shooting north. If you're shooting south, it ends up landing to the left. That's one type of Coriolis force. Another type, it has to do with altitude. Now this is like if you're above the Earth, let's say you're I don't know, like 100 feet above the Earth, and you're maintaining ground speed, you're maintaining the same position over the ground, you're traveling faster than the ground is because you have to go a full, 2 pi r, but the r is the radius of the Earth plus that extra distance. So as you change altitudes, if you're above the ground by a certain height, you're traveling faster than the ground is. If you were to fall, you would land slightly east of the point just below you. That's what the Coriolis effect is. To say that it's fake or it doesn't exist just isn't true. Anybody can actually measure this. If you're on like a merry-go-round, you can walk around in a circle just fine, but if you try to step straight in or straight out, you sort of feel this force kind of kicking you off to the side. That's this idea that you're actually moving faster than the ground, so when you hit the ground, it kind of skids a little bit. Just try it if you don't believe it. But the important thing is to understand what it is, so that you could properly debunk it. To say that it doesn't exist or anything like that, it's just not true. Okay, gyroscopes. This, I think, is actually fairly intriguing. This is the concept that gyroscopes, like on planes, for example, don't seem to track the rotation of the Earth. It's interesting. I think it's worth looking into. But we don't have to... So here's the idea. Like, we've already talked about how the rotation of the Earth is actually incredibly slow. 24 hours... It takes 24 hours to rotate once. That is a very slow rotation. What you need to do is, if you want to somehow prove that gyroscopes prove that the Earth is not rotating, you have to find out what the minimum detectable rotation is for that gyroscope. So you should be able to contact the manufacturer, or maybe there's a spec sheet online. There'll be some sort of idea, there'll be some sort of concept of sensitivity. I'm not sure what sort of units it'll be in, but the point is, you should be able to look that up. You know, it's lazy to make a sort of a hand-waving argument when all the data's there. So first I have to find out, should that sensor be able to detect such a small motion? Alright, so I have a problem with this also. A lot of videos I've seen, people will use a soundbite from this guy who works at NASA, and he's like, it is Photoshop, but it has to be. And they always repeat it 4 times, and it's like, it is Photoshop, but it has to be. It is Photoshop, but it has to be. It is Photoshop, but... this idea that a composite image is not a valid image is flat wrong. You know, people are used to like holding up a camera and taking a picture, and like, what do you think is actually going on inside that piece of equipment in your hand? You know what? There's a pixel array, a sensor array. Each sensor measures a certain number of counts, which is based on the brightness. So the point is that all your camera is doing is taking raw data. So if you were to look at that, it'd be a whole bunch of numbers, right? Every pixel value has a red, green, and a blue value. Then it is converted into an image. And if instead of using a camera, if you were to use if you were to have some data, let's say, because this is what the guy was talking about, they had satellite data that measured like phytoplankton in the ocean. So they basically, if you think of it, they have a map of the oceans with a whole bunch of numbers all over it. Because they didn't have good, apparently, because they didn't have good images, they decided to use that data set to create a sort of a pseudo image. The problem comes in, they have to convert those numbers into a color, right? So someone had to make a decision that, okay, if the phytoplankton is between like 10 and 15, we're going to use this color blue, and if it's between 15 and 25, we're going to use this other color blue. That's where the problem comes in. That's where you might not want to trust it. Like normally you would calibrate it, right? You would have some photographic images where you could say, well, according to this image, a phytoplankton count of 16 produces this color, green or blue. Then you could use that calibrated data to calibrate your image. But the point that I'm trying to make is that the simple concept of creating a composite image using data, there's nothing wrong with that inherently. It can be wrong if you do it incorrectly. But if you think about, that's all your camera is really doing anyway. There's really no difference. I've had to do work using infrared sensors where I wasn't producing an image per se. I was collecting counts of IR data. I could then take those numbers and convert it into an image to get an idea. It's just to visually represent it, really. But anyway, I would avoid the argument that if it's a composite image, then it's flat out wrong, or that it must be fake, because it's not true. Here's another big one. This idea of cold moonlight. I see it all the time. And here's something that, okay, first of all, I need to explain this, that what temperature is. Temperature is the average random kinetic energy of the molecules in a particular substance. Okay, that's sort of a fancy way, well, a long-winded way of saying that the molecules in that substance are sort of moving randomly like that. And as energy is added to it, they move faster, and we feel that as heat. How heat transfers. There's only 3 different ways that heat can transfer. Okay, it can transfer through conduction. That is that when an object is touching another object, the heat in this object can transfer into this. Right? So this is like, you have like all your molecules are, moving around, like vibrating, and as they're bumping into the molecules here, those start moving and vibrating, and there's also convection. Convection is related to conduction, only it uses fluid. So what happens is you have some hot object, the air around that object gets heated up through conduction, and as the air heats up, it expands and moves out of the way, and then colder air takes its place. So you get these sort of like currents where heat is then transferred from the object to the air, and then those currents can then transfer heat elsewhere. It's pretty much conduction. It's given its own name because of the concept of the fluid moving, but really, other than that, the only other way energy can be transferred from an object is through a concept called radiation. And this is kind of an interesting thing if you've never heard this before, but we've all seen like iron glowing orange, right? The reason why it's glowing that color, that particular color orange, is based on how hot that object is. Okay, so if the object was even hotter, then it would radiate energy at a shorter wavelength, right? And that's actually how the sun gives off light. The surface of the sun, according to the round earth model, 5,500 Kelvin or so, it gives off a yellowish green light right around 550 nanometers. If the sun was colder, then it would give off more orange light or more red light. Okay, the same exact way that our bodies give off infrared light. Like if you've seen like Predator, right? You can see like body heat. But it's all based on the same concept. It's a concept called black body radiation. It's well understood. I've used it in my lab many times. The concept of black body radiation. Okay, so all that to say is, those are 3 ways that energy can be transferred from an object. There's only those 3 ways. Okay, so how do you measure temperature? Okay, now the way a thermometer works, when you hold a thermometer up to an object, like let's say like an old school like mercury thermometer, you hold that up to an object, the heat is transferred into the object through conduction. If you hold it there long enough, it'll eventually reach equilibrium, so it has the same temperature as the object. And now you have some tube with mercury in it, with tick marks on it where you've calibrated it in a laboratory, so that as that mercury increases in temperature, it expands, and then you can read off the temperature along all those tick marks, right? But the point is that there is no magic way to just measure temperature. The only way you're going to measure temperature is through one of those methods. So where they get this idea of cold moonlight, okay, there's sensors that you can go buy them probably at Home Depot. I'm not exactly sure where you pick them up, but when you point them at an object, they tell you the temperature, and they give you that temperature based on the black body radiation curve. Okay, it's not touching it. You're not holding it up to it. You're trying to measure the temperature from a distance. The only way that can work, and I bet you if you contact the manufacturer, maybe it's proprietary, maybe not. You probably find out more information about it. But my guess is, actually, let me get the whiteboard for this. Okay, so the black body radiation curve kind of looks something like this, where this height is you can think of it as the brightness, how much light and then along this axis is wavelength. So when an object has temperature, like our bodies, for example, we give off light along a whole bunch of different wavelengths. The peak of that wavelength is related to our temperature. So at like 98.6, this peak is going to be at some particular color, right? As objects get hotter, their black body radiation curve kind of goes like this. The hotter an object is, the colder an object is, it kind of goes down like this. It's complicated, but still well understood. So I suspect if you were to contact the manufacturer, what they would tell you is that they use a 2-color infrared sensor what that does is it measures two different values in the infrared. So somewhere out here, so let's say that like this region is infrared. Well, if I were to take a sensor like this, point it at an object, and tell you how bright it is at one particular wavelength in the infrared and another, so you need two different data points, you can then calculate the slope of that line. That slope would tell you the temperature of that object. Right? If the object was hotter, you would have a steeper slope. Okay, all that being said, okay, I know this kind of sounds like a rant, but there is no magic way to measure temperature. Temperature is measured through one of these processes: conduction, convection, which is just conduction, or radiation. Those sensors use radiation. It's a light sensor. It is measuring how bright something is in a particular wavelength. I suspect those use a two-color IR sensor. It then gives you the estimated temperature based on the slope between those 2 points. Now, what happens if those colors are messed up in some way, right? If when you're pointing it at that object, you're not only measuring the infrared that it is emitting, but you're also measuring a component, some extra infrared that is being shown, like shined onto it. It would screw up all your actual measurements. So I would suspect that that's exactly what's happening, that the light coming off the moon, when the sunlight reflects on the moon, a lot of those different wavelengths are absorbed. It only emits certain wavelengths. When it then shines on an object and is reflected off that object, it's probably some extra components in the infrared. I am never finishing this fucking video. Anyway, so my point is, though, you can't rely on a sensor to give you valuable data unless you understand how that sensor works, because you might be using it in a regime that sensor was never designed for. Contact the manufacturer of those temperature sensors. Ask them questions. Find out what the wavelengths are in the infrared sensors that are used. Find out under what circumstances it would give you bad data. But most importantly, if you could measure the temperature in some other fashion using a thermometer, I would highly recommend that. Here's something else. This idea of there is no thrust in space. That is ridiculous. I don't know where people are pulling that out of. A plane with a propeller on it will not work in space, because it is grabbing air and throwing it backwards, and that's how it gets its push forwards. A jet engine will not work in space because it sucks air in to a turbine, speeds it up really fast, shoots it out the back, and that's how you get the push forward. But a rocket has its own propellant with it. In like a rocket that's used by like NASA, let's say, assuming they aren't faking things, they have hydrogen and oxygen. It burns and creates water and a whole bunch of energy. That energy is then used to propel those water molecules out the back. That's what gives you the thrust forward. It's a pretty simple concept. So I don't exactly understand like how people get to the concept that there's no thrust in space. I wrote down this idea of equal and opposite reaction just to make sure that people understand what it means, because I've heard people invoke this concept of every action has an equal and opposite reaction incorrectly. Just keep in mind that this idea of equal and opposite has to occur on two different bodies. Okay, this is the equal and opposite reaction would be that if I throw a heavy bowling ball, I impart an energy of force onto that bowling ball. The equal and opposite force is on me. Okay, it has to be on two different bodies. If the equal and opposite force were to occur on the same body, what that means is nothing in the universe could ever move. We'd all be locked in place, right? Because there'd be an equal and opposite force on everything. Okay, here's something else too. So I saw that Cody's lab did an experiment in the vacuum, in a vacuum chamber, where he tried to ignite gunpowder, and he was having trouble getting it to burn. People are now using that to say, well, see, because you can't burn gunpowder in a vacuum, that means that it's impossible to ignite rockets in space. And that's a false equivalence. There are two different situations. In a rocket, the fuel is ignited in a enclosed chamber. There's a rocket nozzle where all that energy is then forced out of, but that enclosed chamber gives you a limit on how much vacuum there. Terrible way to explain it. First of all, you need to understand what's going on. Basically, the reason why gunpowder works and ignites so fast is that it has its own oxygen with it, so that as it ignites, it releases oxygen, and that way the burning is not being limited by how much oxygen it has, right? So when you're trying to build a campfire, you might blow on it to get it to burn faster. That's because you're providing more oxygen to it. Gunpowder works where the combustible and the oxygen are there in the right proportions, so that it's not dependent on having extra oxygen, so that it burns super fast. Okay. Now, in a vacuum, what's happening is, as soon as that oxygen is created, the vacuum sort of sucks it away. It's pulled away faster than it's pulled away so fast it doesn't have time to combust. If you were to try to fire a bullet, and we should contact Cody's lab and have him do this experiment in a cartridge, right? As the ignition begins, oxygen is released, but it's held in place very, very close to all the gunpowder, so it would be available for the chain reaction. So this is the idea. So anyway, the point is that you're not taking hydrogen and oxygen in space when you're firing a rocket. You're not taking hydrogen and oxygen, putting these two masses together and trying to light it. They're enclosed in a tight space with a very, very small opening exposing it to the vacuum. So it's not the same thing. Something else that bugs me all the time, people will show these photos that NASA shows of the Earth, whether or not they're fake. Let's assume for a second that they're real photos. And because there is a reflection of the sun, you see this sort of like spot, this bright spot, which is a reflection of the sun. Because there's that spot from the sun on the surface of the Earth, people will say, well, look, there's a hot spot. There could be no hot spot if the sun was, 93 million miles away. I don't know what you mean by hot spot. It's not a hot spot. This is the problem of just pulling things out of your ass. It's a reflection. You get the same thing on anything, like a piece of cardboard. It doesn't have to be a shiny mirror finish. But anyway, it's not a hot spot, whatever that means. It's a reflection, and you'd be able to see it doesn't tell you whether the sun is far away or close. You'd see the same thing whether it was far away or close. Okay, here's something else too. This idea of planes taking off and landing, or like a hot air balloon. This is the idea that once you leave the Earth, you can leave the Earth, and if you just stay in space, the Earth rotates underneath you, and then you can land and you're in a different part of the Earth. It's the same exact concept when they talk about planes being able to take off and land. How can they do that if the runways are moving? This is a concept that was actually... This was an argument that was actually used in the Flat Earth mockumentary. It was used in that because it's a joke. But again, everything on Earth is moving at the same... Everything around you is moving at the same speed in the same direction. So constant linear motion can't be detected. Like, there's no way to detect if if you're in a train and the train's going 1,000 miles per hour, it feels the same as if you're sitting still. There's no way to tell that you're actually moving. If you're moving along the surface of the Earth, let's say you're on the equator, 1,000 miles per hour, you leave the Earth, you're still moving at 1,000 miles per hour, so you keep up with the ground. I don't want to beat a dead horse here. I've already talked about this, but I'd stop using the argument. It's not a good one. I think I already mentioned this, but this idea of 8 inches per mile squared, you have to include height. So I'll put up an image that shows you the full equation for calculating it. Okay, this one is a big deal. It drives me nuts every time I see it. People will talk about perspective, right? Let me use a whiteboard. So this is when you're like, if you're looking down a hallway and parallel lines appear to converge at what's called the vanishing point. Let's see if I can draw this. This is a terrible drawing. The hallway. Anyway, okay, so what I'll see is there'll be some drawing in a video where it shows a person and it has these perspective lines, right? And then it says like they cross somehow at the horizon, and then the lines keep going, and that somehow explains why objects drop below the horizon. Talk about pulling something out of your ass. This is what I mean when I say just like using your intuition. Like, you think, well, objects appear to be dropping or rising as they get further away, therefore they'll continue to. So like it's but think critically about this. Where is the vanishing point? It's at infinity, right? So every object past infinity will be in this area. It's ridiculous. I don't even know what else to say about it. Please, for the love of God, stop showing that. It is the most retarded thing ever. Again, now that you know this, stop using it. It makes you look stupid. Anybody who understands perspective, which is a lot of people, artists, anyone who understands like physics, there's a lot of people out there understand the concept fully. They're going to see that and they're going to laugh. And if your only goal is to indoctrinate idiots, then keep using it by all means. But if you're seeking truth, now that you know that that is a stupid thing to say, stop using it, please. Here's another one. This is related. This is the concept of corpuscular arrays. You know, the same people who will use these arguments about perspective, they do understand the concept of parallel lines appearing to not be parallel. And then like in the very next breath they're talking about these corpuscular rays. Okay, this is the idea of sunlight shining through clouds, and the rays that come through the clouds appear to diverge, so that you can then trace them back and find out where the sun is. That's one idea. And the other idea is that those lines should be parallel. If the sun is infinitely far away, those lines should be parallel. And you're right, they should be. The problem is that you don't have all the information. You have no information about depth. Okay? You don't know, when you see those pictures, right, where you've got like clouds and the sun behind the clouds, and then you see these rays, you don't know how far away from you that sun is. Okay, so you're only measuring, let's just say, like X and Y, but not Z. So if you now, I'm not trying to, you can still use that concept to prove that the sun is not infinitely far away or really far away if you get more data. So what I would recommend is try to get a third perspective. I don't know how easy this is going to be, but if you could find out, if you could get a picture of these rays coming through the sun, right, and then you got a separate perspective, so somebody standing From this point of view, if you can get a photo of that, and then you can get somebody from the point of view of the camera, from a different point of view, so you can get this extra piece of data, this sort of depth, this z distance. Because when you're looking at it from this direction, if you're this guy, you're only seeing like x and y. Without that depth component, you have no idea if these lines are actually parallel. Okay? That's the whole point. We all know that parallel lines can appear to not be parallel if they're changing their depth from you. You want to use that argument, it's only good if you get the extra information, because it's still easily explainable while having the sun really far away. That's all I wanted to say. In the round Earth model, okay, the North Star and all the stars around the North Star, if you were to take a long exposure video, you would see that the stars are making circles. Okay, and those circles get bigger and bigger and bigger until you reach the equator. Then from the equator, all the stars make straight lines. So they rise in the east, they go straight overhead, and they set in the west. Then as you go south of the equator, they move in circles, but circles around the South Pole. Okay, you should be able to, you don't have to go to the South Pole to measure that, right? Anywhere south of the equator, anywhere in South America, you should be able to measure the same thing, like long exposure times, watch the stars. I would say that that's something that that anybody should be able to do. Now, it doesn't necessarily prove that the Earth is round or flat, but at least according to the flat Earth model that I've seen, what you would expect is that the stars make circles around the North Pole, and those circles just get bigger and bigger and bigger the further south you go. The next thing that I want to talk about is what I find intriguing or very sort of interesting about the whole flat Earth argument. I'm just going to plow through these because this video is way too long. I do like the sort of conspiracy theory story of like Admiral Byrd, doing expeditions in South America, Operation High Jump, and then then there's like we immediately signed a treaty with all these nations, and they started firing nukes right up into the sky, and like Operation Fishbowl. That story is interesting. It's intriguing. Everything sort of seems to fit. I think that's ultimately what got me interested in all this to begin with, because the normal mainstream explanation doesn't seem to make sense. So it sort of paints the picture of a conspiracy, which, I don't know, if you're into this sort of thing, it's pretty cool, I guess. I know that there's lots of evidence of NASA fraud, going all the way back to the Apollo programs, all the way up until now, the space station. So I find that intriguing too. For some reason, we're being lied to by NASA. Just keep in mind, proving that NASA lies does not necessarily prove that the Earth is flat. There could be other things going on. There could be other reasons why NASA's lying. The whole concept of gyroscopes not tracking the rotation of the Earth, I find that very intriguing. Again, I mentioned earlier in the video that you should contact the manufacturer of these gyroscopes, find out if they're even sensitive enough to detect the rotation of the Earth. But I do think that that's intriguing. I think it's worth tracking down. The whole concept of like the flight paths not making sense, I think that's incredibly intriguing. There was somebody, traveling to LA, and they had to make an emergency landing. They were coming across the South Pacific, I guess, from the direction of Hawaii. They had to make an emergency landing, so they landed in Alaska, and that makes no sense on the round Earth model. The whole concept of flight paths, I find that intriguing as well. I think it's worth looking into. Again, it doesn't prove that the Earth is flat. There could be other things going on, but it's worth looking into. I think it's a valid area to pursue because you might actually find something. Okay, this is, if you haven't seen the lunar wave videos, there's a YouTube channel called Crow 777 or Crow 777. Check out his lunar wave videos if you haven't seen it. The best evidence I've ever seen that there's something fishy going on with the moon, even to the point that the moon might even be fake, like a hologram. Very interesting. I've actually looked at this whole lunar wave thing from all the different angles. Needless to say, I have convinced myself that the phenomenon that he is recording is not happening in our atmosphere, that it is happening on the moon itself. So I would go check that out. Very, very intriguing, and it might play into the rest of this stuff. I'd already mentioned the whole like North Star, and then how if you go to the southern hemisphere on the round Earth model, you should see circles. I think that's an intriguing area to investigate, because you should be able to at least validate what the round Earth model says or disprove it. That should be an easy thing to do, because you should be able to find somebody in South America. You don't necessarily have to fly there if you can find somebody you trust. And then probably the most interesting thing that I think that people should be trying to investigate, which nobody is this concept of the horizon lowering as you rise up. I think that's a valid area to pursue, and that sort of brings me to the last part of the video. How do you prove flat Earth? Alright, this monstrosity of a video is almost finished. So, here's how you can prove the flat Earth model, prove or disprove it. A couple things. Now, according to the flat Earth model, right, the sun makes small circles during the summertime, during the wintertime makes much larger circles. You should be able to, if that model is correct, you should be able to measure the speed of the sun. I mean the actual speed, the angular speed. So, how long does it take for it to pass 10 degrees, right? So if you can get a degrees per second that the sun is traveling. Again, that number should be faster in the summertime than it is in the wintertime. I already talked about going south of the equator and doing some time-lapse photography, and like measuring if the stars are circling around the south celestial pole. But here's the most important thing, I think, because anybody can do this. Measure the horizon dropping as you go up in height. They put up a quick picture again to show you the equation that you use. Here's the deal. When you first start running the numbers about, like, should you be able to notice the horizon dropping, and the number of degrees is pretty small, like even up in a plane, right? However, if the number, it doesn't matter if the number is small. What matters is do you have equipment that is sensitive enough to measure it, okay? And check this out. This is pretty neat. If you have a typical camera, let's say, 35 degrees field of view, and it has 4,000 pixels in the vertical, okay? If you go up 800 feet, all right, which is the height of a tallish, like, skyscraper, like 75-story or 60-story building or something like that, which they have those buildings everywhere. If you calculate how many degrees should the horizon drop at 800 feet, that equates to 57 pixels in a camera. You should be able to measure that. In fact, I think anybody should be able to measure this. Now, I just want to say this, that you can probably convince yourself with a level and a camera, maybe a tripod, go to a nearby city, get up onto the roof of a tall building. You should be able to convince yourself if the horizon has actually dropped compared to when you're on the ground. But if you want to convince the world, if you want to get a video of this and put it online and convince everybody, you're going to have to be more scientific about it. So the first thing you have to do is you have to align a level with your camera. Okay, now you can do this if you buy a piece of like aluminum, attach a level to the piece of like aluminum and attach the camera to that. You want to make sure that the mount, which is this piece of metal I'm talking about, you want to make sure that the mount itself is not flexing. You could use perhaps something like this to reinforce your mount. You can purchase these at like Home Depot, but a nice solid piece of metal, maybe reinforce it with a couple of these sort of spines going down it to stop it from flexing. Attach your camera to it, attach a level to it, so that you know that when you're looking at the level that the camera is in the exact same position. That the whole point is that you want to be able to make measurements over and over again, so that you know that if the level is flat, that the camera orientation is the same each time that level reads the same thing. Now, the best thing to do would be to have two cameras, point them in opposite directions, align them, right? So what you could do is put it on a tripod at a certain height, okay, align it with a level, put a mark like on a wall in a room, and set the mark at the same height as the camera. In one camera, you want that mark to be in the center of the image, and then rotate the tripod and verify that the other camera is also right, has that spot right in the center. Okay. If you want more information about this, I'd be glad to help. Send me an email or something. Maybe I can make another video that would describe how to create such a mount. What the purpose is that if you can get, see, if you show in a camera that the horizon was at a certain pixel level, and then you go up in a building and now that horizon is lower, how do you know the camera isn't tilted? Well, you can sit there and you can read the level, but the best way would be to have two cameras pointed in opposite directions. If you're tilted, if the horizon has dropped on one, it should raise on the other. Okay, so the whole goal would be to be able to have two cameras aligned so that they're perfectly pointing straight, and you can go to the top of a tall building, 800 feet or so, measure the horizon, show that it is below the center of the image, and actually show it simultaneously in both cameras. Hopefully that makes sense, but if you're looking for one experiment that you can do that would definitively prove whether the Earth is flat or round, that is how you do it. Anybody can do it. So I think that's the one thing this whole like internet conspiracy theory is missing, is definitive proof. I don't know why nobody's done this yet. People have attempted to do it. Like I guess the main reason is that like nobody's done the calculations and figured out that a normal handheld camera is sensitive enough to measure that drop. So I'm excited about seeing what the results are. Maybe if I can get to a nearby city. Also, it would be best if you could go to a tall skyscraper that's like along a coast where you can look out over the ocean in two different directions. That'd be the best way to do it. But anyway, so there you go. That would be how you prove it. Get accurate measurements. It might turn out that the horizon does not drop at all. If that's the case, then the Earth is flat. Maybe the horizon drops, but not as much as the round Earth theory would predict. Well, that would indicate that the Earth is much larger than we've been told. Or alternatively, the horizon drops exactly the amount you would expect it to, in which case, then I would say the Earth is in fact round. So, anyway, yeah, this video is finally over. Huzzah!